Acids and bases are two of the oldest terms in chemistry. They go back to the 17th century, which is quite a long while, right? Originally, these categories were created and things were categorized into them based on just observations of their properties. Acids, for example, are generally good at dissolving things that you might not think of dissolving readily, like rocks or hunks of metal, things like that. Okay, there's some other properties associated with them that folks use to sort out the original allocation of things into one category or the other. Our modern definitions are based on molecular properties, just what's happening in the solution. What are the things that are present in a particular solution that makes them act like acids, okay? One of those molecular properties is that when you mix an acid and a base together, it eliminates the properties of both. You can't have a solution that's both an acid and a base at the same time, okay? So our description in terms of molecular properties has to be consistent with that. It has to say, okay, this is why those two things couldn't coexist. That reaction in which an acid and a base react and eliminate the properties of both of them, that's called neutralization. Okay, because if we get the quantities right, we get rid of both the acid and the base, and we end up with what we call a neutral solution, meaning it is neither acid nor base. Our definition we're going to use for our purposes in this class is what is known as the Arrhenius definition of acids and bases. Okay, and in that definition, an acid is something that dissolves in water to form an increased number of what we call hydronium ions, or H3O+, okay? Bases dissolve in water and form an excess of OH- or hydroxide ions. And so we talk about them in terms of the ions that they form. Let me make a comment about the acid part. We also sometimes will write this as just H+, okay? Most chemists, myself included, are fairly inconsistent about whether we write H+ or H3O+. So just pretty much just have to get used to that idea that those are essentially the same thing, right? If you think about it, H+ stuck onto a water molecule becomes H3O+, right? And so that's the distinction between those two things. If those are the definitions of the two different categories, then why can't they coexist? What is our neutralization reaction going to be like? Well, it says we pour together a solution that has H3O+ ions in it and a solution that has OH- ions in it. Those ions have opposite charges, so they're going to naturally be pulled together. And when they do that, those two ions can react with one another and just give us water, all right? And so that's why our mixture of acid and base will become neutral, is because when an acid and a base react with one another, what they tend to do is to produce water. Okay, that's what a neutralization reaction amounts to, largely independent of what the acid and the base are. Okay, there's sometimes some other things that hang around in our equation, but that reaction right there, we could call that, if we want to be fancy, we could say that's the net ionic equation for the reaction between what in a few minutes we'll define as a strong acid and a strong base. Not even a few minutes. So here comes our definition of what it is to be a strong or weak acid or base. Okay, so a strong acid is one that is, for any practical purposes, completely dissociated when it's in solution. All right. So hydrochloric acid is a strong acid, right? And so HCl is hydrochloric acid over here. HCl is kind of interesting. It's a gas as a pure substance. And then so to produce a solution of HCl, we take that gas, we bubble it into water, the water absorbs a bunch of the HCl, and when it does that, what happens is in the solution, the HCl molecules get pulled apart through their interactions with water. We end up with H3O+ ions and chloride ions, okay? The fact that we write this with our normal, what is the arrow we've used for everything so far, what in this video I'm going to refer to as a one-way arrow for reasons that will become clear. That tells us that we believe that essentially every HCl molecule that we put in there is going to get torn apart and break into ions. So if I could swim around in that solution and look to see what kinds of particles were around, I would see H3O+ ions, I'd see chloride ions, and I'd see a lot of water molecules, but I wouldn't find any HCl molecules, okay? When I say there's no molecules, is that literally true? That's a difficult thing to assess, right? But there's no meaningful number of intact molecules. So we talk about this as being a complete dissociation. And that's what it means whenever we say something is a strong acid, that means it dissociates completely. This is just like a little molecular cartoon of what my solution of HCl might look like. So the blue background there is meant to just be a lot of water molecules, all right? Again, the molarity of pure water is like about 55 moles per liter, which can be figured out from the density and the molar mass. And a normal solution is, you know, what, maybe on the order of 1 molar HCl or something like that. The concentrated solutions are up to about 12 molar for the sort of syrupy stuff that we buy to dilute to make the solution. So there's always a lot more water than anything else. We generally don't try to put the water molecules in pictures like this because they would overwhelm everything. Here we see, if I look in that solution, I see H3O pluses and I see chlorides, but I don't see any HCl's, which in this case would be like a, I guess, a white ball and a green ball stuck together, okay? So again, there's none of that in there because it is a strong acid. There are also weak acids, right? Weak acids are ones that dissociate only partially. All right, I will maybe in live class show another little snippet of the video with the conductivity apparatus where we'll see that a solution of a weak acid conducts electricity a little bit, like better than pure water, but not as well as the solution of a strong acid, and that proves that it's got fewer ions in it. The usual example in a textbook, and our textbook is no exception, for a weak acid is acetic acid, which has this formula over here. Right. Acetic acid is the acidic component of vinegar, is one of the things that it shows up in, right? CH3COOH there, that reacts with water. And what happens is that this H on the end here is removed and sticks itself onto the water molecule. That makes an H3O plus ion from the water, and it turns my acetic acid molecule into what is then called an acetate ion, CH3COO minus. That two-way arrow on there, what that means is that not all of the acetic acid molecules are going to fall apart. In actual practice, very few of them are going to fall apart. It's going to stay mostly on the left-hand side as whole molecules. But writing it with that two-way arrow says there's going to be some kind of equilibrium set up where we'll have some things on both sides of the equation when the reaction kind of just settles in and is no longer making progress in one direction or the other. At the very end of the semester, the last week or so, we will learn how to calculate how much of the acetic acid would dissociate. But for now, we're just going to say that a little bit of it would dissociate, a lot of it would stay behind on the left-hand side, okay? And that's what it means to be a weak acid, is the dissociation is not complete, it's only partial. So again, if I could swim in my solution, what do I see now? The picture is a little bit more complicated, but I see that in my solution, I've got a bunch of still stuck together acetic acid molecules. In this case, I've got one here and one there and one up there, I guess. I've got an acetate ion here, and I've got an H3O plus ion over there, okay? I have to always have the same number of positive and negative ion charges in my solution, right? So in this case, since they both got +1, -1 charges, they have to be equal in number. And that's just because I can't have a macroscopic sample of something like a solution in a beaker that has a net electric charge on it. It couldn't stably exist that way. One little comment here, this piece, the COOH piece, that's an example of what, gosh, in chapter 2 of your textbook, we sort of briefly introduced the idea of a functional group. That COOH piece is one of those, and it's a functional group that tends to make things act like weak acids. And so if I ever see an organic molecule that has that COOH on the end of it, one of the first things I'll do in my mind is say, okay, that thing definitely has weak acid properties because it's got that group there. All right. This one is a little bit confusing to students because the fact that it ends in OH here will sometimes trick people into thinking that it should be a base because OH is the ion, OH minus is the ion associated with bases. So be a little bit wary of that and the fact that it doesn't actually make it a base, that this thing is our weak acid. So strong acids, there's just a few. That list right there is all the strong acids that there are, okay? The first three are all hydrogen halides, right? Things, hydrogen bound to things from group 17 over there, the halogens, right? Then I've got a few others there. The ones that you'll see in chemistry lab most often would be HCl hydrochloric, HNO3 nitric, and H2SO4 sulfuric. Those are the most frequently used laboratory reagents of those. There are some things, and HF, hydrofluoric acid, is a good example of this. That is officially a weak acid because it does not fully dissociate. It is, however, very reactive and very dangerous stuff. Hydrofluoric acid, for one thing, will eat glass bottles, and so it has to be kept in Teflon bottles. It's very serious business if you get physically exposed to HF. You won't find that in any of our teaching labs because it's just really nasty. Okay, but that doesn't mean that it's not a weak, it is still a weak acid, but the fact that it's a weak acid doesn't mean it's just safe to handle. Also note that calling something a strong acid doesn't mean that it's got a high molarity, right? HCl is a strong acid if it's at 5 molar concentration, or if it's at 0.05 molar concentration, it's still a strong acid just because it completely dissociates in solution. Okay, so make sure that distinction and the reason behind that distinction makes sense to you. A little bit about bases. The same strong and weak ideas work for bases as well. Okay, and we do the same general thing, like the arrow is a tip-off of what's happening. Okay, strong bases are generally going to be metal hydroxides that dissolve in water. Sodium hydroxide and barium hydroxide are two of those. Right? I wrote here sodium hydroxide, which gives me only 1 OH minus per mole of NaOH. Barium hydroxide, because barium is in group 2, so it's got a +2 charge. That means barium hydroxide has 2 hydroxides. So when it dissociates, it comes apart to make Ba2+ and 2 OH minuses. All right. If I had written out an equation for dissolving the H2SO4 on my strong acid list, that one would make 2 moles of H3O+, or 2 moles of H+ for every mole of H2SO4. So do watch out for that, and we got to make sure we do our stoichiometries correctly when we work with things like that. Weak bases, again, will only dissociate partially. By far, the most commonly encountered weak base is ammonia, NH3. This one is a bit of a stumper for a lot of students because you see NH3 there, and if anything, it looks more like it would be an acid than a base, right? Because it doesn't have any OH group in it. It doesn't seem obvious that it could be a base. So where does the OH minus come from if NH3 gets dissolved in water? Again, ammonia as a pure substance is a gas. Bubble it through water, a lot of it dissolves. My ammonia molecule can interact with a water molecule, and what happens in this case is I'm taking an H from the water and the ammonia is pulling it away. When it does that, H+ goes from the water to the ammonia. I get NH4+, an ammonium ion, and I get my OH minus, my hydroxide ion. So that's how it gets to be a base. Is because that ammonia can tear one of the hydrogens off of the water molecule, and that will leave it as a hydroxide ion, and that gives it its basic properties. Right? Ammonia you'll recognize as being used in a lot of cleaners. Right? Windex, other things like that have some ammonia in them. You can smell the ammonia if you use those things to clean anything, and that's because the basic properties actually are pretty good for cleaning up certain kinds of things that often occur as like things like oil from fingerprints, stuff like that. If you ever, well, you're not working directly in chemistry labs this semester, you're having online labs, but if you were working in a chemistry lab and you ever spilled some, say, sodium hydroxide on your fingers, you would feel that it's kind of slippery and slimy and feels a little like soap. And that's partially, that explains why it's used to clean things, because it has similar properties. All right, the last thing I want to talk about in this segment is a bit more about acid-base reactions or neutralizations, okay? When an acid and a base react, this is a category of reaction that you should be able to write the products for just from knowing what the reactants are generally, all right? So when an acid and a base react, the products are going to be water and what is called generically a salt. So my first simple example here will be if I reacted HCl and NaOH, because those are the two most commonly encountered laboratory acid and base respectively, okay? If those react, I'm going to make water. Water is H2O. So where's the H2O coming from? H2O is also HOH is a way of saying that, right? So that's my H from here and my OH from there. So that's my first product. Then the salt is essentially whatever's left, whatever the other ions can make, right? So in this case, that is literally table salt because it's sodium from the base and chloride from the acid, all right? So that's my acid and base make water and salt. But this is true in general for whatever kinds of acids and bases I want to be making, okay, want to be reacting. So suppose instead of doing, suppose I keep my HCl here. Actually, suppose I'll do nitric acid. I'll do HNO3 just to be different, okay? And now for my base, I'm going to use the other one that was mentioned in my strong acid slide. I'm going to do barium hydroxide, BaOH twice. Now, I still want to make water, so I get H2O. I need to make a salt, which is what are the other ions? The H is from here, the OH from there, so my other ions are barium and nitrate, all right? So I have to make barium and nitrate. Now, to make the barium nitrate, I have to do a little bit of thinking about what are the charges, right? Barium is in group 2. That tells me it should have a 2+ charge. The other thing I know is right here, I've got barium hydroxide. So if I know that OH is OH minus, I've got 2 of those to offset the barium, so it has to be Ba2+, right? So that's Ba2+. The nitrate here is bound to just 1 hydrogen. That means it's NO3 minus. All of that tells me that I need 2 of those. And right now my equation isn't balanced, so I need to put a 2 here and a 2 there as well, I think, to balance my equation. And now I have a balanced equation for the reaction between nitric acid and barium hydroxide, all right? Along with combustion reactions, acid-base reactions are the other category that there's enough generalizability that you should be able to say, I take the acid and the base, I'm going to get water for a product, and then I'm going to take the other ions and make whatever ionic compound those things could make. And that's going to be what we call the salt.